Greetings, class. Have you ever paused to think about a real scientific mystery? I mean, the fact that literally everything you can touch, see, or interact with, all solid matter, is completely dictated by an unseen, incredibly fast-moving cloud of particles called electrons? It's wild. The way these invisible particles arrange themselves determines the shape, structure, and reactivity of our entire universe. Today, we will study electronic structure and ionization energy. Here is our agenda for this explainer. 1. The electronic structure basics. 2. Rules of electronic configuration. 3. Evidence from the unseen. 4. Defining ionization energy. 5. Trends and quantum jumps. And finally, 6. A high-yield summary and conclusion. Let's dive right in. Section 1. The electronic structure basics, energy levels, and shells. We've got to establish our baseline straight away with a core definition: principal quantum shells. These are the highly specific regions outside the nucleus where electrons are found, representing exact energy levels. Okay, let's break this down. Electrons don't just float around randomly. They exist outside the nucleus in these specific energy levels, or as we just defined them, principal quantum shells. Think of them almost like layers of an onion. We number these shells based strictly on their distance from the nucleus. The absolute closest shell is n equals 1, then shell n equals 2 is further out, and n equals 3 is even further away than that. Now here's an absolutely crucial energetic relationship to keep in mind. Electrons closer to the nucleus actually have less energy, but, and this is a big but, they are held much more strongly because of the pull from the protons. On the flip side, outer electrons have way more energy, but they're held a lot less strongly.
Here are the core details regarding this topic. Review them intently for their being crucial for your finals.
Now, these shells can't just hold an infinite number of electrons. There are strict mathematical limits. The first shell, n equals 1, maxes out at just 2 electrons. The second shell, n equals 2, can hold 8. Move to the third shell, n equals 3, and that capacity expands to 18. Finally, the fourth shell, n equals 4, can hold a massive 32 electrons. The rule of thumb here: electrons are always going to fill that lowest energy shell first before they ever move outward. Section 2. Rules of electronic configuration. Arranging the electrons. So electronic configuration is quite simply the formal arrangement of electrons in an atom. And as I just mentioned, electrons always fill the lowest energy shell first. Let's actually trace this. Hydrogen has just 1 electron, so its configuration is literally just 1. Helium fills that first shell completely with 2. Then we get to lithium. It has 3 electrons in total, so the first shell takes 2, and that leftover 1 goes right into the second shell, making its configuration 2, 1. Beryllium steps up to 2, 2, and boron hits 2, 3. Following that exact pattern, we'd go from carbon at 2, 4, right through nitrogen, oxygen, and fluorine until we hit neon. Neon has 10 total electrons. The first shell takes 2, the second takes 8, it's completely full, a perfect 2, 8. But what happens when we hit sodium with 11 electrons? Well, we have to pop open a new shell, so we get 2, 8, and 1 in that third shell. Jumping ahead to chlorine with 17 electrons, we expand all the way out to 2, 8, 7. You might be wondering, why do we even spend time studying this specific arrangement? Well, these breakdowns, like lithium at 2,1, neon at 2,8, and chlorine at 2,8,7, dictate absolutely everything about how an element behaves. Configuration is the master key to understanding chemical reactivity and bonding. It tells us how ions form and explains an element's exact position on the periodic table. The real secret here is stability. Elements with full outer shells, like neon at 2,8, are highly stable and basically unreactive. Compare that to sodium at 2,8,1. It's got that one lone, dangling outer electron that it desperately wants to get rid of, which makes sodium highly reactive. Section 3. Evidence from the unseen. How we know it exists. Now, scientists can't exactly look through a microscope and see an electron. So how do we know all this? We need hard experimental evidence, and that evidence comes primarily from 2 things: atomic emission spectra and ionization energies. Let's talk about the spectra. When atoms absorb energy, their electrons get excited and literally jump up to higher energy levels. But they can't stay there. When they drop back down to their lower, original energy levels, they release that absorbed energy as specific colors of light, Because the energy gaps between shells are exact, we get unique colored lines that form an element's emission spectrum. It's like a chemical fingerprint. This brilliant bit of physics proves, without a doubt, that electrons occupy highly specific, fixed levels, not just random chaotic positions. Section 4. Defining ionization energy. Removing electrons. This brings us to a massively important concept, first ionization energy. The exact definition is the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. I really want to emphasize the word gaseous here. It is absolutely vital to the formal definition. Basically, this is the physical measurement of how tightly an atom is gripping onto its electrons. Let's put some numbers to this using calcium. We start with gaseous calcium, which yields a gaseous calcium 1+ ion plus that removed electron. The delta H, the first ionization energy, is 590 kilojoules per mole. That is exactly the price in energy you have to pay to rip away that very first electron from a mole of gaseous calcium atoms. Section 5. Trends and quantum jumps. Successive removals. Now, what if we want to steal a second electron? To go from a calcium 1+ ion to a 2+ ion, the second ionization energy is 1150 kilojoules per mole. The energy requirement has practically doubled. And this next part is wild. If we try for a third ionization, removing a third electron to make it calcium 3+, the energy required violently spikes to 4,940 kilojoules per mole. Just a massive, enormous jump. So what exactly is going on here? Let's codify the trends. First off, ionization energy will always increase for successive removals, every single time. When you remove a negative electron, your overall ion becomes more positively charged. This means the remaining electrons are pulled in and attracted way more strongly by the nucleus. Because of that tighter grip, it takes progressively more energy to remove the next electron. So the first ionization energy is always less than the second. And that sequence just keeps going. First is less than second, which is less than third, which is less than fourth. But a gradual increase doesn't explain that crazy 5,000 kilojoule spike we just saw with calcium, right? Well, sometimes you get these absolutely huge jumps. This happens specifically when you've managed to completely strip away all the electrons in an outer shell. To get the next electron, you have to dig into an inner shell that is much closer to the nucleus. Because those inner shell electrons are so strongly attracted to the positive core, you need a massive amount of additional energy to break them free. So, whenever you're looking at a data table and spot one of these giant numerical jumps, it's a dead giveaway that you've broken into a brand new principal quantum shell. Let's look at sodium and nitrogen to really hammer this home. Sodium is 281, meaning it has exactly 1 lone electron in its third shell. Once it loses that single outer electron, the very next one has to be ripped from that full, stable second shell. Bam! That causes a huge energy jump between its first and second ionization energies. On the other hand, nitrogen is 2,5. It has 5 outer electrons in the second shell. You can remove those 5 with a steady, predictable increase in energy. But after all 5 are gone, that next electron has to be pulled from the deeply embedded first shell, and that causes a massive jump between nitrogen's 5th and 6th ionization energies. Section 6. High-yield summary and conclusion. Key examination points. Let's wrap this explainer up with a high-yield summary. 1. Electrons arrange themselves in specific principal quantum shells around the nucleus. 2. These shells have strict mathematical capacities, 2, 8, 18, and 32. 3. This electronic configuration is the ultimate cheat code. It completely dictates chemical stability and reactivity. 4. Ionization energy is the exact measure of energy needed to remove gaseous electrons. 5. Successive ionization energies always increase continuously. 6. Those dramatic energy jumps, they confidently indicate you're breaking into inner shells. And finally, 7. Emission spectra and ionization energies provide the rock-solid proof that these specific electronic structures actually exist. We've seen today just how tenaciously an atom holds onto its innermost electrons, requiring thousands of kilojoules of energy just to break shell n equals 1. But I'll leave you with this provocative thought. If removing mere electrons from the first shell demands such massive, incredible energy, what unimaginable, world-altering forces are required to split the positively charged nucleus itself? Keep exploring, keep questioning, and I'll see you in the next explainer.
Key vocabulary related to this topic is displayed, sorted according to multiple exam boards. These words require serious attention during preparation because of their importance and must never be neglected. In addition, analysis of past paper is provided for each exam board and paper style. Focus on this carefully as it will greatly assist in improving your preparation. Try to understand the context and practical use of each keyword rather than learning them by heart alone. Frequent practice with these terms in past questions will enhance your accuracy and overall performance.
Please subscribe our channel to get more educational videos. Thank you.